Chapter 1, Section 1.1, A Review of Calculus. In this video, we want to review calculus, which will be used greatly in our study of kinematics and dynamics and energies in Mechanics 1. We want to start off by defining a function. One of the things that we take for granted in physics is that the world can be modeled very reasonably by mathematics. Thus, a good understanding in mathematics translates to a good understanding in the physical world. We will be using functions of real variables to model the physical world in this course. In our case, a function will be a mapping from the real numbers to the real numbers. Thus, we will have an input space and we will have an output space. And these will both be in the real numbers, such that one input gets mapped to one output. This can be modeled by this set notation here, but it can also be modeled in a number of different ways. First of all, we can model it through a graph. In mathematics, we typically use an x-axis on the horizontal and a y-axis on the vertical. On the x-axis, we have a set of real numbers, and on the y-axis, we also have a set of real numbers, since our function maps from the real numbers to the real numbers. From here, we can get a function. It could usually be a curve, something like that. And this would be f of x. And that is how we can model that graphically. Something important to note is that a function needs to pass something called the vertical line test, which says that any line that I can draw at any x value will pass through the function once. If it passes through twice, then it will no longer be a function. However, the same cannot be said of horizontal. We can still have a function even if our horizontal line passes through multiple times. In math, again, as I said, we can use x. However, in physics, we will usually use t as our variable. So we can model functions graphically, but we can also model them through formula. For example, we have that y equals f of x. Thus that our f of x values correspond to our y values. Here's an example. We can have y equals the cosine of x, such that for every x value, we can take the cosine of that x value, and that will return our y value. Graphically, this will return a cosine wave, which looks something like this. And it will continue as it fluctuates as a wave. We can also have an exponential function. And we can continue to go crazy with all of these different function types. We could have the cosine of the exponential to the log base 2 of x to the third power. And that would also be a function as well. Okay, so now that we have a strong understanding of functions, we will now transfer our knowledge into building up the notion of calculus, which again, we will be using heavily for this. So one of the main cornerstones that we deal with calculus is the rate of change. So with these functions, I'll draw one graphically again. So say we have a function that looks like this. This is a parabola. This could be x squared, maybe. And if we want to find the average rate of change, Well, we will find 2 points where we want to find the average rate of change between. So we could be there and there. So here we would have x1, here we'd have x2. And these would each correspond to their own y values. We'd have y sub 2 and y sub 1. And this would correspond to some secant line that we have that we can approximate the curve with. This I will call m bar, which will correspond to average slope. And this will be between x1 and x2, it will be delta y over delta x, which is y2 minus y1 over x2 minus x1. So that is how we can find the average rate of change. However, in calculus, we want to deal with something called the instantaneous rate of change. So if I draw another function, and here I'd no longer want to find the tangent line, I want to find the secant line, well, then we will need to utilize some other methods in order to find this. So something that you would learn very early on in a calculus class is something called a limit. So what we will do is we will make the difference between x sub 1 and x sub 2, we will make it 0, so that this secant line keeps getting closer and closer to a tangent line. So how do we do that? Well, what we're going to do is we're going to take a limit. So the definition that I want to create is that we will take a limit as delta x goes to 0 of delta y over delta x. And to do this more formally, we're going to introduce the little difference between x sub 1 and x sub 2. We're going to call that h. So this will become the limit in function notation as h goes to 0 of f of x plus h minus f of x over h. And that is the definition of the derivative. That's how we find the instantaneous rate of change. So now for the derivative, we have different notations that we can use. So the most common is df by dx. This is given that our function is f, and this is equal to the derivative of f of x. And we can also write this in a more compact way. We can write this as f prime of x, or as I like to do, and many physicists like to do to really compact things, f dot. So that is the notation that we can use for derivatives. So now I would like to cover some differentiation methods that we can use. So now that we have the definition, we can really find the derivative of any function. However, using this limit definition gets tedious. So let's try to find the derivative of, we will find the derivative, or first I'll just write the definition one more time. So we have df by dx is equal to the limit as h goes to 0 of f of x plus h minus f of x over h. So now let's try to find the derivative of x. So example, find the derivative of the linear function. So this is equal to the limit as h goes to 0 of, so f of x plus h is just going to be x plus h minus x over h, which is equal to the limit as h goes to 0 of h over h, which is equal to 1. So thus we have found that the derivative of x is equal to 1. Now let's think about this geometrically, because if I draw a graph of the linear function, well, by definition, because every x value corresponds to the same y value, our slope is going to be 1, right? And if you remember that the family of linear functions is f of x is equal to mx, the coefficient m is equal to the slope. So for any function that is linear, d by dx of ax is going to be equal to a. That's just saying that the slope of the line is equal to the derivative, which makes sense. Okay, so now that we've generalized that, we can go over one of the most important rules that we have in differential calculus, which is called the power rule. So I'll throw in another definition. Say I want to take the derivative of some function, x to the n. So if I take this derivative, we assert that this is going to be equal to nx to the n minus 1th power. Okay, and this is something that is very easy to apply. So let's do an example. Let's take the derivative of x squared. So what we do is we find out what our n is. N is going to be 2, because we've got the 2 in the exponent. We get 2 times x to the 2 minus 1th power, which is equal to 2x. That says that the derivative of x squared is equal to 2x. Okay, now we have a couple more definitions that we want to get done, just so that we get all of our different derivatives that we have. If I take the derivative of e to the x, that is going to be e to the x. So the derivative of e to the x is itself. That's a very important fact that we have. And we can generalize this such that the derivative of e to the ax is equal to a e to the ax. Likewise, we also have a differentiation rule for the natural logarithm. It says that the derivative of the natural logarithm of x is equal to 1 over x. For trigonometric functions, we have 2 more rules, such that the derivative of the sine of ax is equal to a times the cosine of ax. The derivative of the cosine of ax is equal to negative a times the sine of ax. Okay, so now that we have all of these different differentiation rules, we would like to cover some of the properties of the derivative that we can use to exploit. The first is the property of linearity. The property of linearity says that I can define a linear combination as a, some constant, times f of x, plus b, some constant, times g of x, such that a and b are in the real numbers. So we can exploit this linearity to say that the derivative of a times f of x plus b times g of x is equal to a df dx plus b dg dx. We can exploit this linearity to define the product rule, which says that if I want to take the derivative of any product of functions, f of x times g of x, that is equal to df dx times g plus f times dg dx. Furthermore, we have another rule that we'd like to define called the chain rule. And this rule states that if I wanted to take the derivative of a composition of functions, f of g of x, well, then that is going to be equal to f prime of g of x times g prime of x. I just threw a lot of definitions at you, so why don't we do an example? So let's say that with the chain rule, I would like to take the derivative of f of x equals sine of x squared. We're going to need to use the chain rule because we see a composition of functions. X squared is the inner function, is sine of x squared is the outer function. So we need to take the derivative of the outer function. So the derivative of sine is cosine. So f prime of x is going to be cosine of x squared, but we also need to multiply this by the derivative of the inside function, which is 2x. That's an example that we have there. Okay, so that pretty much covers it for derivatives. There's another fairly important thing that we should cover, which is just the application of derivatives graphically. We were talking about how derivatives were the instantaneous rate of change. So if we have functions that look like this, very high order polynomial here, we know that if our instantaneous rate of change is 0, then we have a horizontal tangent line. So we'll have a horizontal tangent line here, we'll have a horizontal tangent line there, we'll have a horizontal tangent line there, we'll also have a horizontal tangent line there. Why is this important? Well, this tells us the local maxima and minima of our function. So setting the derivative equal to 0 allows us to find local extrema of our function, which is very important. Something else I should cover is that we do have higher order derivatives. So if there exists f of x that is differentiable and continuous, well then we can keep differentiating to get f prime of x and f double prime of x and f third derivative of x, keep going. And this just entails the continuation of taking these derivatives. Okay, so finally, I would like to cover the opposite of differentiation, which is antidifferentiation. Antidifferentiation is where we know our derivative, but we want to find the original function. So if I take a function, say 2x, and I differentiate it, and it becomes 2, well, then I can also start with 2, and I can anti-differentiate. Then we're going to get something like 2x. But something important is that with an antiderivative, we don't know if there's a constant there, because the power rule will eat up the constants. So if I had here 2x plus 3, the derivative would still be 2. So if I take the antiderivative of 2, I will get 2x, but I don't get the plus 3 at the end. So what we need to do is we need to add a plus c, which is the constant, such that our antiderivative is going to be a family of curves. Okay, so we call this process of reverse differentiating, we call this the process of indefinite integration. So instead of saying, so we have the process d by dx of f of x equals f prime of x. We likewise have the process that the integral, the indefinite integral of f prime of x dx is equal to f of x plus c. Okay. So this is an important rule that we have, and all of the rules that we covered in differential calculus have their same reverse rules in integral calculus. So for the chain rule, we have the rule of substitution, the change of variables rule. And for the product rule, we have the rule of integration by parts. Those two rules we won't be using in this course, but we will be using another rule called the reverse power rule. So the definition of the reverse power rule is that the integral of x to the n dx is equal to x to the n plus 1 over n plus 1 plus c. And that is the reverse power rule, or the power rule for integral calculus. So I've been talking about indefinite integrals, and this is the process of anti-differentiating, but we also have definite integrals, and this takes another graphical approach. So with the derivative, we had the graphical approach that we were finding the instantaneous rate of change. But in integral calculus, we have the fact that we are trying to find the area under the curve. So how can we do this? So let's say that we'll go to a new page. So that I have a graph, that I have a function, and I want to find the area between here and here. Okay, so how do I do this? Well, a nice way to do this is to divide this into many little rectangles, a discrete number of rectangles. Then what I will do is I will sum all of these rectangles and I will find their areas. So how would this happen algebraically? So I would find the area by taking the sum over I of f of x sub I delta x. And this little guy is going to be the delta x, and the height is the f of x sub I. At our certain I value. Now to make this a continuous area, to make all of these rectangles turn into tiny little slivers that will just add up, we're going to take the limit so that we have infinite rectangles in there. So the area is really equal to the integral between I, and we will take the limit as n goes to infinity, and we will start at I equals 1, we will end at n, and this will be of f of x sub I delta x. And this is equal to the definite integral between a and b of f of x dx, such that we're finding the area between a and b. To evaluate these integrals, we can make use of something called the fundamental theorem of calculus. So definition for the fundamental theorem of calculus, we say that the integral between a and b of f of x dx is equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. So that is going to allow us to find the area under the curve. All right, let's do an example. Why don't we find the area under the curve x squared between 0 and 1. So to do this, we will take the integral between 0 and 1 of x squared dx, and the antiderivative of x squared, if we use the reverse power rule, we get 1/3 x cubed. We evaluate between 0 and 1. So we can neglect this 0 term because that's going to be 0 anyways. If we plug in 1, we get 1/3. So the area under x squared between 0 and 1 is 1/3. So this is essentially integral calculus in a nutshell. And integral calculus is actually quite a lot trickier than differential calculus, simply because the process of anti-differentiating is a lot more complicated than it is for differentiating, because we don't always have all of the rules and we need to make use of a lot of creative little tricks. But you'll use that in your calculus course, and we will likely come back to that in mechanics too. But for now, we can use integral and differential calculus to solve equations. We call these equations differential equations. So I'll show you an example of a differential equation. And we can use integrals and derivatives to solve these equations. So let's see. Let's say that we have a case where dy by dx is equal to f of x. This is a very classic differential equation. In this equation, we can use the separation of variables to solve it. So the separation of variables actually allows us to do something which will make mathematicians very angry, which is treat the derivative as a fraction. And this Leibniz notation that we're using, the dy by dx notation. So when we use the separation of variables, again, we treat this like a fraction. We get all of the x variables on one side, we get all the y variables on the other side. And these little differentials that we have, the numerator and denominator of the derivative, are going to count as x and y variables. So what we want to do to get all of the x variables on one side, we want to multiply everything by dx. So then we get dy equals f of x dx. Okay, so what do we do from here? Well, now, in order to get y, all we need to do is integrate. So we're going to take the integral of dy equals, which is, the integral of dy is equivalent to the integral of 1 dy, which is equal to the integral of f of x dx. So thus we have y is equal to the integral of f of x dx plus c. And that is how we deal with separable differential equations. So we'll be dealing with that a lot when we try to derive the equations of motion for 1D and 2D and n-dimensional kinematics in the next video. So that is section 1.1, which is a review of calculus. Thank you.